So our last speaker in this session is Philippe Carpentier from ESRF Grenoble, and he's the expert in high pressure protein crystallography. And he will tell us about his HPMX beamline, I think.
Can you hear me? Oh, it's okay. Thanks for that. First, I would like to thank the organizer for the opportunity to talk about our high pressure method that we are developing at the ESRF in complement to the diffraction beamline. So the high pressure freezing laboratory for macromolecular crystallography, shortly HPMX, is located inside the MX village, sector 30 of the ESRF. The purpose of the lab is to prepare light gases derivative of protein crystal to answer specific questions in structural biology. It's a sample preparation lab, so users have access inside to benches, tools or instruments to handle the sample, and also the different high pressure cells that I will talk about later. A simple search in the PDB revealed that there is more than 1,600 structures containing light gases. So this important number showed the potential interest of studying light gases in structural biology. Of course, number of this protein has been crystallized with the gas naturally present inside the structure. But for many of them, the gas has been needs to be introduced on purpose, and it is the aim of the HPMX service to prepare this gases derivative for the users. And concerning the applications, pressurized noble gas can be used as a probe to map tunnels, channels, or cavity inside or at the surface of a protein. In this case, it's a complementary tool to software like Caver or MOL. We can use also pressurized non-neutral gases such as molecular oxygen to study their activity with a specific protein. High pressure can be used also to induce and to explore conformational fluctuation of protein. Concerning methodology, the high pressure freezing cell can be used to flash cool protein crystal without cryoprotectant, or to produce noble gas derivative for protein structure determination. Sample preparation for the high pressure freezing machine is relatively similar to that for classical X-ray crystallography. We use specific HP pins, which consist of pluggable assembly, which can be connected or disconnected inside liquid nitrogen, and constitute a spine standard sample holder. We fish the crystal with a capillary at the extremity of the pin directly in the drop of the crystallization trace. So the protocol is the same for all the pressure cells. After fishing the crystal, the pin is loaded inside a thin vertical tube here at the top part of the tube. The tube is connected to the pressure cell or the pressure system. And then the bottom of the tube is plunged in liquid nitrogen to cryo-cool this extremity. And the crystal is soaked inside the pressurized gases for typically 10 minutes to produce the derivative. And after that, the pin is released to be flash cool at the bottom part of the tube, still under pressure. After depressurization, the pin is extracted from the tube in liquid nitrogen, reconnected to the base, and stored in a sample changer box. So this slide shows the different gases available for the high pressure freezing. We offer the main noble gases in addition to molecular oxygen, carbon dioxide, and we are designing currently a pressure cell for methane. The soak and freeze methodology allows to process the crystal inside the phase diagram of the different gases. This to produce the derivatization state and to stabilize the derivatization state. And this slide shows pictures of the different pressure cell that we have conceived according to the thermodynamic properties of the different gases. It can be a very complicated system. So quickly, we have a pressure cell for helium, argon, krypton, eventually xenon, in addition to molecular oxygen, carbon dioxide, and we are designing a pressure cell for methane. So now I'm going to describe in a little more detail some scientific example. The first scientific example concerns the study of internal tunnel inside hydrogenase. So this enzyme catalyzes the cleavage of molecular hydrogen into 2 protons. So hydrogenase are, most of the hydrogenases are sensitive to oxygen, but this one from Ralstonia is oxygen tolerant, so it's interesting for application. The active site is buried inside the protein, it's a nickel iron active site, and connected to the surface via hydrophobic tunnels that allow for the transport of both the substrate and the harmful oxygen. These complex internal tunnels were deciphered using krypton labeling at the HPMX lab. And with this approach, we were able to, the users were able to identify an impressive series of 19 krypton inside the anomalous map. And with this, it was possible to trace accurately, precisely, the internal architecture of this hydrogenase from Ralstonia, which comprise two tunnels, 2 entrances, and 2 branches. Further comparison between the different hydrogenases showed that oxygen-tolerant enzyme has, in average, less, shorter, and narrower tunnels than the sensitive one. And the properties of the tunnels of this hydrogenase are described in this paper. The second example concerns a tRNA modifying enzyme, NIAE. And this enzyme is a redox enzyme which catalyzes the hydroxylation of selected tRNA, which has an adenosine in this position. And this tRNA modification appears to be crucial for the survival of few bacteria. The structure consists of a 4-alpha helix bundle with here a d-iron active site buried inside the fold of the protein. So molecular oxygen need to diffuse via a dedicated pathway in order to reach the active site and makes the reaction possible. This specific pathway has been mapped out using krypton labeling at the HPMX lab. And in the anomalous map here, we have identified a line of 4 kryptons, and this line stands along the axis of the 4-alpha helix bundle and fits perfectly one of the tunnels which has been calculated by the program model. And this tunnel was interpreted to be the primary diffusion route for the oxygen to reach the active site. And on the other side, we have here another charge cavity which allows for the docking and positioning of the tRNA in order the hydroxylation here to run. So this has been described in this paper here. And the last example is to show that high pressure can map the surface of protein. And these studies, the aim of the studies was to investigate interaction between noble gases and membrane protein, taking into account possibly the influence of lipids. So it was carried out on 3 typical membrane proteins, but the example described here concerned the bacterial rhodopsin crystal, which has been probed using pressurized argon, and the derivative has been prepared at the HPMX lab under 2,000 bar of argon, and in the resulting structure, an impressive number of 47 argon has been identified in the anomalous map, which bind essentially here the membrane region, the hydrophobic membrane region of the bacteriodopsin. But more importantly, here it was observed that this krypton are competitor of structural lipids and displace the chain of the structural lipid. Further molecular dynamics simulation also predicted that argon bind this region of the protein, but also predict that the argon decrease the dynamic of the protein. So in this paper, the hypothesis that the binding of krypton is similar to or can be the anesthetic action of argon on the bacteriorhodopsin. Concerning recent development, there is a growing interest in studying enzymes that can process pollutant gases or greenhouse gases, like in first instance, carbon dioxide. But carbon dioxide is very difficult to process in cryogenic pressure cell because it produces rapidly carbonic ice. We have designed a new type of pressure cell with a 2-stage to avoid this problem. And it's interesting to see that there is already more than 120 structures deposited in the PDB with CO2 inside. And the first example of use could be and will be actually enzyme that can reduce carbon dioxide, like the CODH, for instance, or enzyme that can incorporate CO2 in another molecule, like carboxylases. It is the case of the enzyme Rubisco, for instance. So, so for the moment, we don't have any highlight for the CO2 derivative, but the pressure cell has been tested on a simple lysozyme. We were able to easily produce the CO2 derivative, and you can see in this very high quality map that we can identify a CO2 molecule inside the classical pocket of lysozyme. And interestingly, we can combine X-ray diffraction with Raman spectroscopy at the ECOS lab to confirm that there is a Raman band due to the vibration of carbon dioxide in the Raman spectra of the crystal, and to confirm the derivatization state, actually. To conclude this slide, so the panel of structure which has been deposited in the PDB owing to crystal which has been prepared at the HPMX lab. It's interesting to see that we have already contributed for the majority of the structure which contain krypton and argon. And to summarize, high pressure has been proved to be useful for mapping tunnels, functional tunnels, cavity and surface of proteins, or to investigate interaction between oxygen and selected proteins. And also, high pressure can aid for investigating structural change or ligand binding process in protein. So to finish, I would like to give you the web address of the lab, 2 reference papers that you can read if you want to have more information. I would like to thank the people involved in the technical support of the lab, those involved in the scientific and technical developments, it's also important to mention that we have close interaction with the team of ICOS. You will hear a talk about that later. And more importantly, you can, if you have a project, and if you think that the HPMX lab can be useful in your project, so don't hesitate to contact us. And with this one, I would like to thank you for your attention.
Thank you very much for this very lovely talk. Any questions? There's a question.
Hello, I'm Phil Leonard from DomainX Limited. Where you looked at PDB structures that contain, for example, CO2.
Yeah.
How confident were you that the depositors had assigned the electron density correctly?
Actually, no, I didn't look about that, but if you, I don't know for the majority of the structure, but if you look like in this one, but actually it's enzyme which process CO2, and here you can see here, I think, here, I think there is a reaction between CO2 and the CODH, but I don't know. But I think in general, it's enzyme which process CO2 and its interpretation of reaction. And but I have to confess that I didn't look at this point here. But you can see here. Sorry for.
Yeah. So Robert here from Cambridge. I'm just curious. When you have a protein crystal with soaked in some atmosphere at high pressure, does it never happen that as you are about to conduct the X-ray experiment, that the gas literally bubbles up and damages the crystal?
Never seen something like this. No. I would say no. But I think you can run reaction or something like this, or make, possibly you can, for instance, reduce the CO2 with the electron produced by the radiation damage. I don't know. Don't know. Never seen something like this either.
Christina Ginovic Carugo, EMBL Grenoble. I have one first comment on the pressurizing with CO2. I think carbonic anhydrase is a very gratifying example to test the system if one needs to do so, where you can see very well the binding, the substrate bound. But I have the question with regards to mapping the channels. So you used, what was it, argon and krypton, right? Yeah. And that was mostly for map more hydrophobic channels, right? Mm-hmm. What would you recommend if the channel were more polar, more polarizable atom like xenon, or what would be your recommendation?
I think they are all the same. They are mapping in priorities hydrophobic region, but it happens that krypton can bind also hydrophilic. Yeah. But you can soak in something else, like, I don't know, chlorine, or it's another type of experiment. But yeah, it's probing in priorities hydrophobic region of protein.
Yeah, Alexander Mingus here, HSU Düsseldorf. I have a question regarding the methane cell you're developing. So first of all, why is it that difficult, or is it difficult to do that? And would it be feasible to infuse, for example, ethylene into your protein?
Sorry, what is difficult?
Yeah, is it difficult to do that? So is it very different from the CO2 cell, for example?
For methane, you say?
Yeah, the methane cell, right? And is it possible, for example, to use it also for ethylene infusion?
I don't know for the moment because I never tried the methane, but I think it's easier for methane than for CO2, for instance, because it's a gas which is easier to process. Yeah. But I don't know what is the question exactly.
Yeah, but my main question would be if it is also possible. So you showed this methane cell you're developing, but could it also be used, for example, for other gases like ethylene, which are quite similar?
Yeah. There's no. As soon as there is an example, I think if you come to me, for instance, with a good project, I can consider to build a cell for the project. Yeah.
Thanks.
I have a question on Slack. Here. James Holton is asking, has anyone tried high pressure hydrogen? You showed that,
no?
No. Not.
No.
Okay.
It's dangerous.
Second part of the question. This could test a hypothesis of hydrogen gas as a mediator of radiation damage.
You don't get the question. If I can use hydrogen as a mediator of radiation damage. No, I don't know. Never tried the hydrogen. So, I don't understand why. I think because radiation and damage are producing hydrogen. So you want to do the inverse, I think.
Yeah, but nobody has.
No, it's too dangerous. I think the safety will refuse to do.
To save the building. I have another question. What is, for example, if you would try carbon dioxide, what would be the resolution range for the crystals? So would you
It's exactly what I'm trying to explain on this slide, because here, of course, you can identify clearly the CO2 because you have 3 blobs, but let's imagine that you have 2 angstrom of resolution. You can combine with Raman, and then you will see the band of CO2. So with the 2 experiments, you will be confident of your. So even if you have 2 angstrom, it's okay. You can find a solution.
Okay.
I was interested in the design of the cell that you have.
Yeah.
So some years ago, there was you could buy a device called a cryo-exciter for making heavy atom derivatives, where you just used a loop. Your crystal was mounted on a standard loop, and you put it under high pressure and then plunge it into a dewar. Now, why is it necessary to have your cell rather than just having a crystal sitting damp in a loop?
I think the idea here is to freeze under pressure. It's the main idea, I think. You have to, when you freeze, you should have the pressure in order to stabilize, because if you pressurize, depressurize, and freeze, for gases like argon, the gas will escape. I think it's too small.
Any more questions anywhere? If not, we're closing this session. Yes. And we're starting again at 1:15. So we have a short break, right? Okay.